Hi fellow enthusiasts, welcome to my channel. Let's go into today's video and we're gonna come back at the end to wrap it up. Earlier in this series we showed this video, an AM transmitter, simple AM transmitter with 3 to 6 components. 3 components in most part because the oscillator itself is just made up of 3 components. And then 6 components because we have to include microphone and the biasing component, which is a resistor and a capacitor to make up the full transmitter. Alright, so this is an AM radio transmitter without coil. Normally in many of our transmitters we used to include tank circuits, so which is made up of a coil and a capacitor in parallel. But in this circuit, as you can see, we just have a 5-5 timer, 5-5-5 timer, a capacitor. This one is a variable capacitor, the yellow colored one. And then we have a resistor. Actually, we have 2 resistors, but this resistor works with the capacitor to bias to produce the frequency we're going to look at in this transmitter. Then the other resistor in conjunction with the microphone and capacitor for the audio input. So we're going to analyze how this works. So let's start by showing the circuit diagram for this. So basically this is the circuit diagram. Right, so you can pause the video and get the circuit diagram. So I'm just going to adjust it for you to see it properly. Basically in our design we use 3.7 volts. So let's just change it up, 3.7 3v7. So here we have the capacitor here, variable capacitor, and I think this is 40 picofarads. Yeah, so the 40 picofarads capacitor, and then the 47 kilo ohms resistor, and these 3 5-5 timer, resistor and capacitor makes up the transmitter. In the demonstration we didn't use this control voltage capacitor, but you can put it in yours. And then the other 3 components are these: microphone, the biasing resistor, and this decoupling capacitor, so that it isolates the DC biasing condition of this microphone from the AC signal produced when you speak into it, when there is a sound on the microphone. So this blocks that DC biasing condition and only couples the AC signal or the alternating or the audio signal from the microphone into the 555 timer. Now you might be wondering how this works. We had a video on how 555 timers work. Please watch out for that video, or go watch that video because we already made the video. There are 2 comparators inside this 5-5 timer, so it's constantly checking the the inverting and non-inverting input voltages, and whenever the non-inverting input is equal or greater than the inverting input, the output is high. So we did some very detailed analysis on that. So that's how this basically works. So there is something here that I need to correct. This value here, this resistor actually goes from this point to the power. Yes, this is the way it should be. Yeah, because it's the biasing. I'm gonna explain how this works, so don't worry about this. So this resistor, sorry, goes to pin 3. So the capacitor here, VC1, is charged and discharged through this one single resistor. It's charged and discharged through that resistor. And so when it charges up to 1/3 VCC, it will discharge. There's a comparator inside that triggers. So it will be switching between two-third VCC and one-third VCC. So when the voltage charges at two-third VCC, it will start to discharge until it gets to one-third VCC and the cycle continues. We have the full in-depth analysis in the other video. Let's not talk about that now. If there's interest, we can go back and talk about it at a later time. But let's just go and analyze the circuit and show you how we determine the frequency and all that. Someone was asking about how to determine the frequency. So let's just go ahead and talk about that right now. Okay. So in this um, view here, let's talk about how to determine the frequency. So I'm just gonna adjust this view. Okay, so that's the circuit diagram one more time. And on the shaded side, we'll try to show a way to improve the amplification or the range, because the range is very limited as it is currently. This circuit didn't work as expected, so we have removed it from the design, but we can improve on it and come back with something. We want to show how we can improve the range, but not so much to disturb your neighbor or anybody, just to show proof of concept. All right, so let's go ahead and analyze the circuit and show you how we determine the value we're using here. You can see 19 to 57 picofarads. How did we determine that value? And this 47 kilo ohms. What is the reason for that? Why did we choose that value? We're going to start by showing you a few concepts, and then we'll go ahead and analyze this one more time. So let's start by showing you this. We we want to build a transmitter that works on the AM band. So you need to know what frequency that AM band covers. It's very important that whenever you're making any circuit, whenever you're designing any circuit, you have a full understanding of what the functionalities are. All right. So basic understanding of what you want to go into um, will help you to be successful. So, and what is that? The AM band is from 540 kilohertz to 1.5, 1.6 megahertz. 540 to 1.6 or 1600 kilohertz, which is 1.6 megahertz. This is the AM band. All right, so you want to design the 5/5 timer to oscillate. You want to design it in an unstable mode to oscillate at this frequency or within this frequency. So what you want to do is you have to know what components are responsible for the oscillation. And in our case, it is the resistor and the capacitor, the R and the C. Now, if you want to build a transmitter that works within a range, then you have to have one of the components that play a role in the frequency to be variable. If they are both fixed values, then the output will be a fixed value. But when they are both variable, then you might be changing one and the other, or you choose one to be fixed and then the other to be variable. In our case, we choose the resistor to be fixed and the capacitor to be variable, but there's nothing that stops you from making both variable, or making your capacitor fixed and your resistor variable, whichever works for you. Now, how do I choose this range? Remember, we know the range for the AM transmitter is 540 kilohertz to 1600 kilohertz. So I'll show you the formula for calculating the frequency, and then you go ahead and plug in the value. Make a choice, choose whatever value that you want to make the fixed, and then calculate the one that you want to make your variable. All right, so let's go ahead and show that. Right, let's go back to the one note because that is where the magic will happen. All right, so let's make this on this side. Again, let me show you this tiny notes here because I think it's important. Oh, we come back to it. Let's come back to it. It is important, but let's come back to it. Let's start by doing the calculation. So I'll give you the formula first. And I say that the astable multivibrator we built is a square wave astable multivibrator. Square wave because the capacitor, the VC1 is charged and discharged. VC1 is charged and discharged through this resistor R1. What it then means is that your charge time and discharge time are equal. And if they're equal, then the on time and off time will be approximately equal. So the time the output is on and the time the output is off will be identical. Let's just do this to mean equal. On time, off time are equal. Okay, so I'm gonna redraw this because I don't think my screen was showing when I drew that. So if this is my amplitude, and this is my time, this is amplitude, this is time. It means that the time my output stays on and the time it stays at 0 will be approximately equal. So let's just use this to mean equal, and so on and so forth, and then the cycle continues. So T on is equals to T off, and in your period is equals to T on plus T off, and your frequency is equal to 1 over T. Your T on is equal to T off is equal to 0.693 or thereabouts RC. Is an important value. Right. Actually, it should be half that value. So T on plus T off. Let's just say that your T on plus T off is that value, or your T is that value, 0.693 RC, and that means that your F is 1 over that value, 0.693 RC. In our case, the C is VC1 and the R is just your R1. Alright, or this could also be written as F is equal to 1.443 over RC. Now, we already calculated the frequency. We already verified, not calculated, but we verified the frequency for the AM transmitter, and we established that it's 540 to 1600. Right, so we've established that. So just go here and say the F high and F low, right? Or F upper limit, F upper is equal to 1600 kilohertz, and then F lower is 540 kilohertz. All right, so that's what it is. Then you can plug this back into the formula, and when you do, you get 1600 kilohertz is equal to 1.443 over RC. Now, when you're designing this, there's no value for R, no value for C. You just pick the value that you have in your kit and calculate for the rest. Fortunately for us, we have a lot of variable capacitors, so we just chose one of the many resistors, literally hundreds of resistors we have. We just chose a value, and we chose 47k. There's no reason for that. We just chose 47k. We could have chosen any other value, but we chose 47k. So 16 kilohertz is equal to 1.443 over 47k multiplied by C. We don't know what that C is, so we just say C is equal to then cross multiplying 1.443 divided by 16k multiplied by 47k. And once you punch this out, you will get a value. So let's get that value. So let's see. Let's use our calculator. So here we are doing 1.443 divided by 1600, and then we have 3 more zeros because it's kilohertz. All right, multiplied by 47, and then 3 zeros. Close that, and then equals. So the value here is about 19.2 picofarads. About 19.2 picofarads. So we go back here and say that C is equal to 19 point, okay, let's just call it 19, so 1919 picofarads. Remember, the value actually is 1.91888. I think 3.8 times 10 raised to power minus 11, right, according to our calculator. So we're gonna move one digit over to the right, and then we increment the number of negatives we're gonna have. So that's how we get there. So when we move, let me use a different color. When we move this decimal one this way, I gotta show what I'm doing. Right, so when we move this decimal from here to over here, then we increment the number of places this has to move. So it has to go to 12. Right, so that's how we got this. And we're doing that because you know that milli is times 10. Milli is times 10. Let's make it black. Yeah. So milli is times 10 raised to power minus 3. Micro is times 10 raised to minus 6. Nano is times 10 raised to power minus 9. Pico is times 10 raised to power minus 12. and femto is times 10 raised to power minus 15. So because our calculator was at minus 11, and we have no name for that, we want to make it either minus 9 or minus 12, so we can call it pico, nano or pico, and so on and so forth. So we want to make it look like one of these. So we just have to shift the decimal to the right one time, so we can make this 11, so we can shift it to the left again. So that's all we did. All right, so let's go back here. So that's how we got 19 picofarads, right? Then let's check this is the F upper. We just calculated F upper, which is this one here. And we're going to repeat the same thing for F lower, all right? And so for F lower, we'll repeat the same formula, 1.443 divided by F lower now is 540 kilo times, remember we're using the same resistor, 47 kilo. So we're gonna plug this into our calculator again. F lower. No, sorry, this is RC. This is RC. So this doesn't go here. We'll just write the formula first. Let's just write the formula. Lower is equal to 1.44 RC. Then F lower is 540 kilo is equal to 1.443 over R is 47 kilo times C, such that if you cross multiply, C is equal to 1 over 1.443 over 540 kilohertz. Let's not confuse that with kilo ohms. Multiplied by 47 kilo ohms. All right. So in this case, then C is equal to, I'm gonna go back to our calculator and we'll clear that 1.443 divided by 540, 3 zeros there, times 47 and the 3 zeros, close that bracket, and then equals. So again, we're getting 5.685 times 10 raised to power minus 11. So we're going to shift this by 1 decimal, and then also add one more zero here, one more decimal place here to make it minus 12. So it's going to be 56.85 or 86, 56.86 pico. So we're going to go back and say that C is 56.86 picofarads. Now I'm gonna go back and show you that table that has or that chart or lookup table that I said we're gonna get back to. So our range is 56.7, or you can call it 57 for the upper, and the lower is 19.9. So approximately between 20 and 60. Actually between 19 and 60. So between 19, or you can go a little bit lower. You can say between 18 and 60 to make sure you covered everything. So this is what I mean. If you want to choose a value of variable capacitor and your range is 19.19 to 56.86, 0.86. This is the range. You want to choose something that bounds this. So you want to choose something from, let's say, 19 or anything lower, less than or equal to 19, to obviously um shouldn't be anything less than this value, less than 56. So you can go 60. You can go 60. So about approximately 60 picofarads. You want to go between 19 and 60 picofarads. So let's see how we choose the value. Goes back to the color codes on the variable resistors. Each of the color codes means something. So there's a range there. The green ones, they range from 3.3 to 8.3. Someone measure this and give the values. So the green one is rated at 5p on the body or on the sachet when you buy them, but the actual value range between 3.3 and 8.3. The white ones range from 5 to 13.7, 5.5 to 13.7. The red ones 20 is rated at 20, but the value is from 6 to 28. The green ones rated at 30 ranges from 9 to 60. Yellow ones rated at 40 ranges from 12 to 60. The brown ones rated at 60 or 70 ranges from 20 to 80. There's another brown one that is rated at 120 picofarads, ranges from 50 to 120. Now, if you have all these values, and I do have all of them, after my calculation and choosing a random R, I was able to, well, not really random in that sense, it was an educated guess. And choosing the yellow one, I knew that this bounds my frequency. My frequency range is from 19.19 to 56.86. So I chose the yellow one. That's the reason for that. So as I vary it, I can cover the entire AM band. That means wherever I am, I can pick a station where there's no broadcast and gradually tune in my variable capacitor to that station. If you have any other of these, let's say you have this, obviously you'll be covering only the upper end of the spectrum. What you need to do is to change the value of your capacitor, of your resistor, sorry. You change the value of your resistor so that this will cover your range. Okay, so that's why we chose the value that we chose. We picked one value at random. In our case, we chose the resistor, and then we calculated the value of the capacitor because we have all the values. We have all the mixed uh, value of capacitors, and we chose one that works well for us. So do the same, pick one and calculate the other. The values for this variable, this biasing capacitor and resist and condenser mic is also based on what we have. And we've used 2K2 several times to bias the condenser microphone, so we just used it again. So experiment and find something that works for you. In the radio that we built, in the transmitter we built, we didn't have the voltage control capacitor that goes from pin 5 to ground. In your case, you can put it in, and in the schematic we have online, we have included that. So do this. Now this 10k resistor you see here, we didn't use it. This 10k resistor is connected to the reset pin of the 555 timer. If you pull it to ground, the 555 timer will stop oscillating. Think of ways to use it. You can use it to mute your transmitter if you wish. So just connect a switch directly from here to ground, or put a capacitor, a transistor, and use a transistor as a switch to shut it off, to squelch it, pause it, and shut it down, or whatever you want to do. But in our case, we didn't use it, so you can um, just ignore it. In this case, it is not required. All right, so let's just go and show the circuit diagram one more time. All right, so this is the circuit diagram that we used. This capacitor was omitted in the final version, so you can also omit that in yours, right? And then You have the 5-5 timer pin 2 and 6 tied together, and then this position, this is an input to one comparator, and this is input to the another comparator. 2 and 6 are inputs to different comparators, and then when the voltage on those pins gets to a particular level based on the value of this capacitor, um, so it's charging through the capacitor, right? So through the resistor, I mean, and then when the capacitor gets to a certain value, the two comparators will switch or toggle the output. One will be charged, one will cause it to be charging, and the other will cause it to be discharging, and it will go between 1/3 VCC and 2/3 VCC. So the frequency continues. Now, the maximum frequency you can get with a 5-5 timer depends on the type of 5-5 timer that you got. Some of them can get up to 3 megahertz, the newer ones. Some of them can get to 2 megahertz, others can get to 1 megahertz. The good thing is the station we're working on, the radio we're building here, the transmitter we're building, is for an AM radio frequency band, which is just between 540 kilohertz and 1600 kilohertz, or 1.6 megahertz. And you saw in our transmitter, the transmitter was actually transmitting to within 1700 megahertz. So the 5-5 timer we're using is the one that can reach about 2 megahertz. Now, if you have the same type, you can use the CMOS versions. If you have the same type, you can get to 1700 megahertz, 1700 kilohertz. Or if you have the other types, the 5 and E555 timers, you can get to maybe somewhere around 1 megahertz. Right. So that's what we did. All right. So build this and let us know the challenges you have, and we can address them in our next video. Try to use this capacitor here and try to amplify this. Now, you can just use this directly to drive a speaker. So you can connect a variable, you can connect a capacitor here at the output. So let's just clone this one here. You can connect a capacitor here and then connect a speaker at the output here. So that's how you can do that. Let's see if there's a speaker we can use here. There's no speaker there. Yeah, so you can take this kind of speaker. All right. Maybe next time we can do a tutorial on how to use this tool to design your circuit. If there's interest, let us know. We can do a quick tutorial on that. All right, so you can just connect it up like this, and you can listen to the sound coming out of the speaker. As simple as that. You can just convert this to it is already an unstable multivibrator, but you can actually hear the sound playing from here. So in the next video, we're probably going to show you how to use the same circuits um as a metal detector. The same exact circuit, if you vary this, you hear different sounds coming from the speaker. We've done something like this before using just as an unstable multivibrator, but with slight modification, you can get this to function as a metal detector. All right. And then you can also try to modify this and have it function as a wireless metal detector. In this case, you won't have a speaker, but you can detect it from your radio. Try to see if you can get that done. And if you need help, we can make a video tutorial on that. But yeah, this is it. Right, a stable multivibrator at high enough frequency from 100 kilohertz and above, the signal will radiate. This is the secret of every transmitter. Once the circuit can oscillate at 100 kilohertz and above, the signal will leave the surface of the wire, will leave the surface of the conductor on which it is, through the skin effect, it will start to ionize the nearest environment, and then the magnetic waves in the nearest environment will create electric waves, and the electric waves will create magnetic waves, and magnetic waves will create electric waves, and it continues in that order until the signal attenuates and gets weaker and weaker and weaker away from the source. So that's what really happens. If you can build anything that will oscillate above 100 kilohertz, from 100 kilohertz and above, there's a strong chance that the signal will start leaving the conductors and start going into the nearest environment. And if the signal is strong enough, that nearest environment will influence the closer environment, and then that to the nearer environment, and it keeps going that way, radiating out from the source. If you have good antenna, then you can radiate it even further. Right, good antenna, good power, you can radiate it further. See how you can connect a transistor here as an amplifier to boost the signal coming here to even go further. Right, so I will just make a suggestion, quick suggestion. So let's try a transistor. Okay, let's pick this one here and just use it. So how would you normally connect this transistor to be an amplifier, to amplify the signal coming from the system? So you can just connect this up this way, and the speaker, the output goes into the base. Normally you can put a resistor there um, to bias it, then connect it up this way. Right, so the let's connect this to the ground. Now, without testing this, I think this should work. You can connect this speaker here or on the, let me just duplicate that. You can connect the speaker here as well, it doesn't matter. You can do either or, and probably try both and see how it works. But you can connect it either at the collector circuit or the emitter circuit. We've done a video on transistor biasing. Try to watch that, and you can put the resistor here. Let's make this look more beautiful. All right. Um, let's give this away a little bit more. Right, something is wrong. All right. So that will be it. And for here, I wouldn't use that value. You can use 220 ohms and see how that works. And then, but how would you connect your antenna to it if you want to connect an antenna? So, if you just want to connect your speaker, let's not confuse anyone. Let's take out one of the speakers because we're just showing possibilities. So you can connect to the emitter circuit or the collector circuit. Now, if you want to connect an antenna, so the let's take out the speaker if you want to connect an antenna, and then connect one more resistor here. I'm going to connect a resistor here, and connect my antenna up from this point. All right. Now, what is the value of this resistor? You want to center the output here. You want to center the value here. So if I have 3.3, 3.7 volts, I want the voltage here to be around 1.75, something like that, 1.75. So you want to center the output um, 1.85, not 75. We want this to be 1.85. Yeah. So then if you maybe we'll have to do another tutorial on transistor biasing and we can explain that better. But if you chose a current IC current or quiescent current of maybe 0.1 milliamp, then you calculate the value of your resistor. So why do I choose the value? I want it to be drawing little to no current when there is no load. So if I do that, so I'm going to find a value for my resistor. If I choose a value of 0.1 uh, milliamp, I know that V is equal to IR. That's so that my R is V over R over I. So 1.85 divided by the I that I've chosen, which is 0.1 times 10 raised to power minus 3. So in that case, my R will be 18.5 kilo ohms. So here I'm going to use 18.5. 18K5. Let's just call it 18K5. So if I use this value, it means at no load, only about 0.1 milliamp will be flowing through this capacitor. So that way I'm centering the output. So try it this way and see what if you can improve the range. Okay. All right. So I think that will be it on this. So if you have any further question, let us know. We can help you to address it. Now just try to be creative, try to take some risks and do these things and see. So let's just change this value. We normally use 2222, but you can use whatever you have. You can, as you've seen, we've used different NPN transistors in our projects and they all work great. So that's your AM transmitter. Now it's a little bit more complex because we're adding amplifier to improve the range. Someone was asking, what's the range? Try different amplifiers and see how far you can improve the range. If you just want to test it for the limited range, remember this is for educational purposes only. So if you want to build this, make sure that you don't interfere with your neighbor's radios. That's why we normally don't put long antennas for transmitters or even RF amplifiers at the output for transmitters, because you don't want to interfere with your neighbors' radios. And also remember that some televisions still use AM frequencies to transmit, right? The some part of the signal, I think the audio signal or the video signal, one of those is AM. So try not to interfere with people around you. This is just for educational purposes, so you can know how things really work. If you want to build them for extended use, make sure that you're operating within the free license band, or make sure that you obtain license if you want to operate one at home. Okay, but just for a student or an enthusiast like me who like to know how things work, this is what we do. I like to know how things work. So this is how it works. So how you bias this then is, as there is variation in the signal coming into the um, control voltage, which is pin 5, that variation will change the amplitude of your signal, and then that change in the amplitude of the signal will modulate. Remember, AM means amplitude modulation. We just modulate it. And then the carrier signal, which is a square wave generated by the 555 timer, is kind of modulated or modified because of the presence of this control voltage. And that value, then that signal is decoded by the radio, and the audio is extracted from the carrier signal, and that's what you hear at the speaker, like so. Alright, so the AM radio transmitter covering from 540 kilohertz transmitter. You're right. All right, so that's the original circuit that we showed that we built, right? So in the actual one, we used 3.3 kilo ohms, but we've used different values. As you've seen, the current one is at 2.2 kilo ohms. So use the values that you have available to you, right? And in the current design, we try to use one that looks similar to what we've drawn um on the one note here. So we've moved around the pins so it looks like so, right? But in the original design, we don't really care about that. We just make sure that we have the right connections. And as you can see here, pin 4, which is the reset pin, has no resistor connected to it. And pin 7 is open. Now, I've drawn this circuit before a long time ago. I think it was in 2002 or so, or 2003 for a friend. When we built electronic signpost and we used 5/5 timer to advance the signals across the signpost, to create a trigger that connects to other circuit, decade counter, and other things that advance the light on the signpost. And I had written 2,6, and it was misconstrued. So I had to fix that. Like as you can see here on pin where you have the resistor and capacitor connection is 2,6. It simply means that 2 and 6 are connected together, right? It doesn't mean 2 or 6, it just means both of them are connected together. So if you see here, 2 goes round and gets to 6, right? And even though the wires are crossing, if there's no red dot or any dot, it means there's no connection, they're just passing. If imagine this as a PCB, and some are on the top of the PCB and some are at the bottom of the PCB, there's no connection even though the wires are crossing. Where there's connection, you see a dot, like here and there. But for this area, there's no dot, so there's no connection. No dot, no connection. No dot. No, actually, it's a good one. No dot, no connection. All right. So build yours and let us know your experience. All right. Thanks for sticking around to the end. That'll be it from us today. Please, if you have not subscribed, do so right now. And don't forget to like and share this video. Until we come your way again with more contents, stay enthused.